Welcome back. Till long day after, today I will discuss ring theory. Today I will discuss ring theory just as a review. But at first I will highly recommend you, if you don't see my previous video, at first see my previous video, see the playlist of ring theory chapter. At first see those videos, then today's video would be so easy. Actually today's topic is, today I will discuss ring theory just as a review. At first I will start ring theory from unit element of ring theory. We all of us know definition of unit element of ring theory. Just as a review, R be a ring, then an element A in the ring R is said to be unit element if in the ring R it has a multiplicative inverse. That means A dot B equal to 1, where A is the unit element in the ring R and B is the multiplicative inverse. And the set is denoted as UR, which is actually set of those elements A in R, such that A inverse exists in the ring R with respect to multiplication. And this set is actually in group theory is called as unit group. All of us know what is the UZ. UZ is set containing the element 1 and minus 1. UQ equal to only Q star, that means set Q omitted with singleton set 0. UR equal to R star means R minus singleton set 0. Similarly, UR cross C equal to R star cross C star. What would be UQ cross Q? Let x1, y1 be arbitrary element of Q cross Q and 1, 1 is the unity in the set Q cross Q. Then by definition of unit, there exists x2, y2 belongs to Q cross Q such that x1, y1 times x2, y2 equal to 1, 1. That imply x1, x2, y1, y2 equal to 1, 1. And from this expression, this imply x1, x2 equal to 1 and y1, y2 equal to 1. From the expression x1, x2 equal to 1 and y1, y2 equal to 1, since x1, x2 and y1, y2 be the member of Q. So, from this expression we can tell x1 is unit element in the set Q, and from this expression we can tell y1 is unit element in the set Q. Therefore, that means actually Q cross Q is Q star cross Q star, because unit element of Q is Q star. That means this would be Q star cross Q star. Similarly, unit element of Q cross R equal to Q star cross R star. Next, if we can to find the unit element of Q cross singleton set 0, then similar to before, this would be, so 1, 0 is the unity in this set. Consider A0 be the unit in the set Q cross singleton set 0. Then there exists B cross 0 such that this is equal to unity 1, 0. That imply AB, 0 equal to 1, 0. That imply AB equal to 1. And from the expression AB equal to 1, this imply B is the multiplicative inverse of A. That implies this A is the unit element in Q. And we all of us know the unit element of Q is Q star, which is equal to actually Q minus singleton set 0. Therefore, the unit element of Q cross 0 equal to Q star times singleton set 0. Okay? OL. That means this is actually Q minus the set omitted with 0, 0. If we find U R cross singleton set 0, this is equal to R star cross 0. Actually, this is means R minus singleton set 0, 0. What is the unit element of Zn? In my previous video, I have seen elaborately. Actually, unit element of Zn is Euler-Phi function. Our next discussion about integral domain. We all of us know what is the integral domain. A commutative ring with unity is said to be integral domain if it is without zeros divisor. We all of us know Z, Q, complex number, Zi, all integral domain. But if we consider Z cross Q cross C, then this is not integral domain, because consider these two non-zero elements whose multiplication is 0, but these two elements are non-zero. So this set contain actually zero divisor, because the definition of zero divisor, AB equal to 0 where A not equal to 0, B not equal to 0. Similarly, but if we consider R equal to Q cross singleton set 0, then this is integral domain, because consider two elements X and Y in this ring, where X is look like A comma 0, this is obviously belongs to this set, this ring, and Y equal to B comma 0, this is also belongs to this set. Then X dot Y means A comma 0 times B comma 0, and to find is it zero divisor or not, we have to show this is equal to 0. That imply obviously AB comma 0 equal to 0, and that imply AB equal to 0, and A and B be the member of Q, and we all of us know Q is an integral domain. So since AB be the member of Q and Q is integral domain, then that imply AB equal to 0 means either A equal to 0 or B equal to 0. So obviously this ring Q cross 0 is integral domain. Similarly, the ring Z cross 0, C cross 0, this type of ring is always integral domain. Similarly, Zn is integral domain if n is a prime number. We all of us know Z4 is not integral domain, because 2 cross 2 equal to 0 in Z4. So Z4 contain divisor of 0. So only Zn is integral domain when n is a prime number. We all of us know this is. At first I will prove Gaussian integer Zi is an integral domain. I have seen Zi always integral domain, but today at first I will prove this, because today's topic is just conceptual. For this, consider two arbitrary elements in Zi and consider their product is equal to 0. That means A plus IB, because Z equal to A plus IB and W equal to C plus ID, A plus IB times C plus ID equal to 0. Now multiply this equation both sides by this its conjugate, A minus IB, A plus ID, C plus ID, C minus ID equal to 0. That imply a square plus b square, c square plus d square equal to 0. And since this is only number, and since we all of us know Z is an integral domain, so obviously Z contain no divisor of 0. That means a square plus b square times c square plus d square, these two number is equal to 0. That means either a square plus b square equal to 0 or c square plus d square equal to 0. Okay, have you understood this? Okay. And a square plus b square equal to 0, from this expression we can tell, since this is the non-zero real number, so a square plus b square always greater than 0, and a square plus b square equal to 0, this is possible when only a equal to b equal to 0. Similarly, c square plus d square, always this number always greater than 0, and c square plus d square equal to 0, this is only possible when c equal to d equal to 0. Okay, therefore obviously Zi is an integral domain. Thus this product is equal to 0 means this is possible only, this is only 0 element, otherwise for non-zero element this is equal to 0, this is not possible. So Zi does not contain 0 divisor. Okay, I hope my all viewers have understood this concept easily. Why Zi is an integral domain? Observation, I will see when Zni is integral domain. We all of us know Gaussian integers are always integral domain, but here the question, which value of n? Zni is integral domain. We all of us know Zn is integral domain when n is prime, but here not. Case 1, consider n equal to 1. Then Zn1 I is contain only 0 element, then this does not contain the key of this ring, so this is not integral domain. Now case 2, consider n is not prime number. As for example, consider Z6i, which obviously contain a plus ib, where AB be the member of Z6. Then Z6i contain the element 0, 1, 2, 3, 4, 5, I, 1 plus I, so on. Okay. And this is obviously not integral domain because consider these two elements 2 and 3. Their multiplication is 0. But 2 and 3 be the both non-zero element of this ring. So these contain the 0 divisor. So this is not integral domain. Case 3, consider n is not prime number. N is a prime number. As for example, consider Z5i. Now consider two elements 2 plus I and 2 plus 4i, whose multiplication is congruent to 0 in Z5. But these two elements are non-zero element in this ring. So this contains 0 divisor. So when n is prime number, then this does not always imply Zni is a integral domain. But when Zn, then This is integral domain when only n is a prime number. Then next my question, for which value of n Zn is the integral domain? This is our question. Zni is integral domain if and only if n is congruent to 3 modulo 4. That means actually 4 divide n minus 3, which imply 4k equal to n minus 3. This imply if and only if n equal to 4k plus 3. Therefore, that imply n equal to 3, 7, 11, 19, so on. For this value of n, Zni is integral domain. That means Z3i is integral domain, Z7i is integral domain. Check it oneself. This always contain no zero division. This is very important. For which value of n, Zni is integral domain. Our next observation, I will see 2 cross 2 matrix with real field. Is it integral domain? Similarly, if we consider 2 cross 2 matrices with real field, this is also not integral domain, because 2 cross 2 matrices with real field, this is not commutative ring. That means if we consider 2 matrix A and B, then AB always not equal to BA, because definition of integral domain, actually at first we have to find the ring is commutative ring with unity. Then it is integral domain if it does not contain the zero divisor. Also, this ring has no zero divisor. As for example, consider these 2 matrices which belongs to this ring, but their product is 0. Therefore, this ring contain zero divisor. That implies this ring is not integral domain. Okay? I hope my all viewers have understood what is the integral domain. This type of example actually very important for any competitive exam. Our next observation is field. What is the relation of integral domain with field? An integral domain is field. Since here the name is field, so the ring is denoted as F. An integral domain is said to be field if every non-zero element of this field has a multiplicative inverse. That means for all A in F, if A inverse exists, then we can tell this integral domain is field. Now I will discuss some example of fields which are field and which are not field. We all of us know actually. Today I will discuss just elaborately. Every non-zero element in the field Z has no multiplicative inverse, because here only multiplicative inverse is 1 and minus 1. Similarly, we all of us know real number, complex number, rational number are all field because UR equal to R star, UC equal to C star, similarly UQ equal to Q star. That means here for all ring, every element has multiplicative inverse. So these are belongs to the field. Gaussian integer means Zi. Is this field? This is UZi. We all of us know this is the set containing the element 1 minus 1 I minus 1 I. Okay? Therefore, Zi is not field because every element has not multiplicative inverse. Now if we consider the ring is Z5i, few minutes ago we have seen Zni is integral domain when 4 divide n minus 3. Here n is 5, that means 4 divide 2, this is not possible. So this is not Z phi I is not integral domain. Actually this is contained 0 divisor, because if we consider this 2 element 2 plus I times 2 plus 4i, this is obviously equal to 0. I hope my all viewers have understood this concept. But if we consider Z7i, then obviously 4 divides 7 minus 3. Z7i is integral domain. Also, here every element has multiplicative inverse. So, Z7i is also filled. Similarly, if we consider Z3i, obviously 4 divide n minus 3 means here n equal to 3. That means 4 divides 0. Here the element of Z3i is look like such type. This is the Gaussian integer of modulo 3. And here actually every non-zero element has a multiplicative inverse. To understand better way, just look the multiplication table of Z3i. Notice here every element has multiplicative inverse. So Z3i is filled. I hope my all viewers have understood this concept easily. How look like the multiplication table? Just notice in better way. Okay? Well, if we consider the ring such type Q cross R, Z cross Q, Q cross C cross R, Q cross C, obviously this type of ring is not integral domain. Since this type of ring is not integral domain, so this type of ring is not filled. Because this type of ring contains 0 divisor of 0, we have seen few minutes ago. But if we consider R equal to Q cross 0, then this is obviously integral domain. Also this is filled, because few minutes ago I have seen units element of this set U Q cross 0 is Q star minus 0 0. That means actually every non-zero element of this set has a multiplicative inverse. Similarly, R cross 0, C cross 0, this is be the example of fit. Now I will see one nice ring, Z root 2. Z root 2, this is actually the set which look like A plus B root 2, where AB belongs to the ring Z. Obviously this is subset of the ring R. And Z root 2, if you check, this is be a subring of the ring R. And since the ring is commutative, that means Z root 2 is commutative. Because if ring is commutative, then their subring is obviously commutative. And 1 is the unity of Z root 2, because 1 equal to 1 plus 0 root 2, which is belongs to Z root 2. That means root 2 is commutative ring with unity 1. And since the ring R is integral domain and Z root 2 is subset of this ring, therefore Z root 2 is also integral domain. Since the ring R is integral domain, that implies their subset Z root 2, obviously this is integral domain. That means this set contain no zero divisor. Now I will see, is this set is filled? This is very interesting. Z root 2 means this is the set of a plus b root 2 where ab belongs to integer. That means minus 1, minus 2, minus 3, so on. 1, 2, 3, 1 plus 2 root 2, 1 plus 3 root 2. This type of set contained in the set z root 2. Then obviously 2 belongs to z square root of 2. If z square root of 2 be filled, then 2 has obviously their multiplicative inverse, that means 2 dot x equal to 1. That imply x equal to half. But half does not belongs to z square root of 2. Therefore, 2 has no multiplicative inverse. That means I have got one element in this ring which has no multiplicative inverse. So, z square root of 2, this is integral domain but not filled. Okay? But if we consider the set q square root of 2, which is look like the a plus b square root of 2 where ab belongs to q, which is obviously subset of the ring R, this is be a field because here every non-zero element has a multiplicative inverse. For this, consider a non-zero element a plus b square root of 2 belongs to q square root of 2. To find the multiplicative inverse of a plus b square root of 2, for this, obviously the multiplicative inverse of a plus b square root of 2 look like 1 over a plus b square root of 2. Now we have to find, is this member of q square root of 2? For this, multiply this by its conjugate 1 over a minus b square root of 2. For this, to cancel 1 over b square root of 2, multiply this by a minus b square root of 2, which is equal to a minus b square root of 2 over a square minus 2b square. Okay? And obviously this is member of q square root of 2. So, multiplicative inverse of a plus b square root of 2 belongs to q square root of 2. Therefore, since this is the arbitrary element of q square root of 2, that means every non-zero element in q square root of 2 has a multiplicative inverse. Okay? That means obviously q square root of 2 is a field, but z square root of 2 is integral domain but not field. Today I will stop here. In my next video, I will discuss ring theory just as a review. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos.